And now for the conclusion. Happy holidays everyone from side A, side B. P15. Can't believe we're here. In this video, ladies and gentlemen, taking care of reflection across the line y equals x. We think we have a very good video, a build-up of 4 proofs, then a final one with a quick example. Like a season finale, we're hoping everything will fall into place. Like the previous video, our proof of the graphs of a function f and its inverse are reflections of each other across the line y equals x will formalize the intuition of how inverses work. The first proof is an extension of the Pythagorean theorem, which we proved in a previous video earlier this year, where we defined a square and a triangle. We want to prove the midpoint formula, but to do that, we'll use the dimensions of a square. Here's what we need to do. We want to duplicate a triangle, then make them into a larger square. The larger square will be composed of 4 congruent triangles. The first thing to do, define the initial components of the original square, which we call the Pythagorean square on the left. Its original dimensions were side length a equals b, thus its area can be defined as b squared blue box. The congruent triangles we're naming T1 and T2, which were formed by the diagonal of the original square. They were defined as right triangles. We're redefining the legs of each triangle as b and b with hypotenuse c. No, wait, not literally. Oh no.
My mission is to protect you.
Who sent you?
You did. 35 years from now, you reprogrammed me to be your protector here, in this time.
This is deep.
Now back to the proof. Each triangle is defined by the Pythagorean theorem as b squared plus b squared equals c squared. Next, we defined a triangle, which we're naming Z, green box, which was formed by rotating T1 relative to T2, yellow arrow, and joining them at their legs, now named B. This created a larger right triangle with legs C and C, with hypotenuse H equals 2B. Second column, we're given C squared plus C squared equals H squared. Second blue bullet, which gives 2c squared equals 4b squared. First off, to prove the larger square is composed of 4 congruent triangles, we duplicate Z into a second triangle and name it Z prime, red box. We rotate it 180 degrees, name its congruent triangles as the following, T3 and T4. Sliding over the blackboard, to form a larger square, we take Z and Z prime, align them along their hypotenuse, H equals 2B. The newly formed quadrilateral is named the Babylonian square. The notation looks a little messy, but it's really not. Now to prove its components. Since Z prime is a duplicate of Z, they are congruent. Because Z is made up of T1 and T2, and Z prime is made up of T3 and T4, all 4 triangles are congruent. First orange bullet. Confirming the formation of a quadrilateral with 4 sides of length C, then confirming the square properties. We have side equality. Second orange bullet. The vertex angles of Z and Z prime, denoted as orange V, highlights the right angle symbol. Both are 90 degrees. Third bullet. The remaining 2 vertex are formed by joining the 45-degree base angles of Z and prime, named A for acute angle. 2 acute angles of 45 degrees are at each corner, noted with 4 yellow hatch marks. Conclusion: a quadrilateral with 4 equal sides and 4 vertex, which are 90-degree angles, is a square. One more component to check. Dimensional verification. Second column, area of large square is c squared. And by the area of a triangle formula, 1/2 times base times height. So the area of each individual triangle 1 over 2 times b squared. Second orange bullet. Since we have 4 said triangles, we have 4 times what we just said, which just equals 2b squared. Last orange bullet. We know c squared equals b squared plus b squared, which returns 2b squared. Since the orange boxes are a match, the sum of the areas of the 4 congruent triangles exactly equals the area of the larger square. Therefore, we have proved all the components of the new square. Nice. Next, we prove the point O is the midpoint of the 2 diagonals, and the diagonals are perpendicular due to the given property. The 4 constituent triangles are congruent. Then consider a square ABCD on a coordinate plane, where the vertices are what we just said. Now consider 2 diagonals, AC and BD. The diagonals intersect at the center of the square, which we called O. Since the square is made up of 4 congruent triangles, orange bullet, which meet at the center O, we can use the CPTCT. Take 5. We can use the CPCTC theorem, which we previously proved, that corresponding parts of congruent triangles are congruent. So by the second blue bullet, the sides of the triangles meeting at O must be equal in length because second orange bullet, such as triangles AOB and BOC, the sides along the diagonal segments are equal, namely OA equals OC. Next orange bullet. For triangles across the center such as AOB and COD, we find OA equals OC and OB equals OD. Second column. Because OA and OC are segments of the diagonal AC, and both are equal, point O must be the midpoint of AC. We can say the same thing for the second orange bullet. Since the diagonals form a linear pair of angles at their intersection, since they are congruent by second blue bullet, both angles AOB and BOC are 90 degrees, showing they are perpendicular. Again, the proof, the diagonals intersect at the midpoint O, relies on the fact all 4 constituent triangles are congruent, and by the second blue bullet, the diagonals are perpendicular at this intersection because the adjacent congruent angles form a linear pair, and each angle is 90 degrees. We are done. Now we want to prove the midpoint formula. To accomplish that, we use the properties of a square. Since we've already defined a square, we can extend the square into the coordinate plane by defining 2 arbitrary points. We let the coordinates of the 2 opposite vertices, say A and C, be x1, y1, and x2, y2, respectively. The midpoint O of the diagonal AC is the point of intersection of the 2 diagonals. We already know the distance from A to O is equal to the distance from O to C. As a consequence, the coordinates of O, which is the midpoint of the line segment AC, must be the average of the coordinate points of A and C. First orange bullet. Now we let the coordinates of O be xy. See that? Next, since O is the midpoint of the horizontal distance between A and C, green box, its x-coordinate must be halfway between x1 and x2. We can express this as x equals x1 plus x2 over 2. Second orange bullet. A similar logic for vertical distance. Red box can be applied to y, then we get the red dot. Second column. Thus, the midpoint formula proven by the properties of a square's diagonals, expressed in the form capital M equals the coordinates green and red dots. We are done. Nice. Now we want to prove 2 non-vertical lines are perpendicular if and only if the product of their slopes equals -1. The first step is to set up the coordinate system, then consider the lines L1 and L2 passing through the origin 0, 0. Let their slopes be M1 and M2 respectively. Next, identify points P1 equals 1 and M1 on L1 and P2 equals 1 and M2 on L2.
What? WOJCIEHOWICZ. What?
The lines are perpendicular if and only if the triangle P1O P2 is any right-angled triangle, with the right angle highlighted as the yellow square. Just one thing before the proof. We can set it up in the following manner because just consider equation 1 and 2 on the left. For any linear functions, we can disregard the b and it won't affect the slope, and both of them will pass through the origin. For example, take a look at lines 1 and 2. Both of them pass through the origin. Then we can plot 2 points, P1 and P2, by letting x equal 1. Observe, both y's will equal their slopes. See that? Which means for this proof, we'll only consider linear equations of the form equation 2 blue box. It suffices to consider the case of a square as a general shape that considers both types of right-angled triangles. Because in case you didn't notice, in the example graph, the triangle is a right scalene triangle, which means its legs are not equal. We get to our first orange bullet of the proof. According to the Pythagorean theorem, the triangle blue bullet is a right triangle with hypotenuse h equals P1, P2, if the sums of the squares of the lengths of the legs OP1 and OP2 equals the square of the length of the hypotenuse. To solve for the values of the Pythagorean theorem, column 1, first bullet, consider 2 triangles. For example, to solve for line segment OP2, we regard it as the hypotenuse for the triangle P lower right. Then, to find the value, we use the distance formula derived from the Pythagorean theorem to solve. In our example, the gold triangle is synonymous with triangle P. See that? Which means triangle Q's base is aligned with triangle P's base, highlighted with the green line. Next, second blackboard, let's substitute values. First, we square root both sides of the distance formula. For triangle P, yellow circle, x2 is 1, x1 is 0, y2 is m2, y1 is 0, which returns, on the right side, 1 minus 0 squared plus m2 minus 0 squared, which just equals 1 plus m2 squared, yellow box. Just do the same logic to find the right side of line segment OP1, red box. Lastly, to find line segment P1, P2, use the following values. x2 is 1, x1 is 1, y2 is m2, y1 is m1, which gives the green box. The next step, just replace the values in the gold box with the values from the yellow, red, and green boxes. Second blackboard. Then we get second orange bullet. Third orange bullet. Left side. Just FOIL the squared expression. Right side. Combine like terms. Notice the terms in the brackets on each side equal each other. Then we can subtract them from both sides. Finally, divide each side by -2, which returns the white box, which shows m1 times m2 equals -1. Therefore, the product of the slopes of 2 perpendicular non-vertical lines must equal -1. We are done. Nice. In the example, the product of their slopes, 2 times -1 over 2 equals -1, which confirms the lines are perpendicular. Alas, the conclusion to the season finale. We want to prove the graph of an inverse function, denoted as f inverse of x, is the reflection of the graph of the original function f of x across the line y equals x, which is based on the fundamental definition of inverse functions. The insight: if a function f maps an input a to an output b, then its inverse function must map the output b back to the original input a.
The world is made up of two kinds of people, twos and ones. Sometimes two ones become a two, and other times one of the ones of a two gets tired of being a two and wants to become a one again. Not that the other one of the two isn't a nice one, it's just that two ones can't be a two without the one.
Oh, for sure. And the inverse has been the main character of the series. But now, we're about to put the intuition, reflection across the line, in mathematical terms. Since the story has been set up, so to speak, by the preliminary proofs, this final proof will be a lot easier. So what's the plan? We believe this can be proven by showing the line segment connecting the 2 points on the square, yellow font, AB and BA, is perpendicular to the line y equals x, and the midpoint capital M of this segment lies on the line y equals x. Now let's get started. The proof relies on two ideas. First, the definition of a function and its inverse. Second, the geometric definition of a reflection across the line y equals x. First orange bullet. A point AB is on the graph of a function f if and only if b equals f of a. This means if the point AB is on the graph of f, then the point BA must be on the graph of f inverse, which has been the hot topic of discussion for weeks. Next, we prove the geometric property of reflection. We need to prove two conditions. First, the midpoint of the line segment connecting AB and BA lies on the line y equals x. Second, the said line segment is perpendicular to the line y equals x. Let's prove condition 1 first. For that, we refer to the midpoint formula, which we just proved, blue box. Second orange bullet, we replace the values of the blue box with the values of p1 and 2 in the following manner. Voila! Observe, ladies and gentlemen, since the x and y coordinate of point M are equal, and because the identity function y equals x preserves the original value x, thus the midpoint M must always lie on the line y equals x. See that? Finally, prove the perpendicularity condition. What? First, case 1. If the line segment of P1, P2 is perpendicular to the line going through M, then if we fold them across the line, the points will match up. Whereas, the second case, we're assuming the lines are not perpendicular, so if we folded the points across the line, they will not match up. So, to finish off the proof, we want to show the line segment P1, P2 is perpendicular with the line y equals x. So how to do that? We refer to the proof we just did. Two non-vertical lines are perpendicular if and only if the product of their slopes equal -1. Second blackboard. To find their slopes, we use the only blue bullet. To find ML, just use the red font. We can use mental math. x1 and y1 will be equal. We can name them C. x2 and y2 will also be equal. We can name them D. Then we have D minus C over D minus C, which just equals 1. Next, to find MS, we do the same. We apply the coordinates of P1 and P2 in the following manner. We get A minus B over B minus A, which equals, after we rewrite the numerator, returns negative brackets B minus A over B minus A, which just equals -1. Last orange bullet, white box. We have the product of the slopes, ml times ms equals 1 times -1, which equals -1, as wanted. Since the midpoint of the segment connecting AB and BA lies on y equals x, and the segment itself is perpendicular to the said line, the point BA is a geometric reflection of AB across the line y equals x. Because every point on the graph of the inverse function is a reflection of a corresponding point on the graph of f, therefore, the entire graph of the inverse function is a reflection of the original function across the line y equals x. We are done. Very nice. One quick example. Consider a function f and its inverse. We have enough information to derive the equation of the line. First, we use the 2 points, 2, 5, and 5, 2, to calculate the slope m, which turns out to be negative brackets 5 minus 2 over 5 minus 2 equals -1. Then, we use the point slope formula. Plug the calculated slope and the coordinates of one of the points, doesn't matter which one. Next, convert to slope-intercept form, which is y equals mx plus b, by simplifying the point slope equation by distributing the slope and then isolating y to find b. Upon doing so, we have the final equation, black box. The equation of the line that connects the points 2, 5 and 5, 2 happens to be L2. To check if the lines L1 and L2 are perpendicular, we just multiply their slopes. We have m1 times m2 equals 1 times -1, which just equals -1, gray circle, which confirms L1 and L2 are indeed perpendicular. The proof translates the intuitive idea of swapping the x and y values into the geometric reality of a reflection across the said line. Until next year, ladies and gentlemen, season's greetings to everyone. That makes sense. The one just goes back to its original one.